The screen you're looking at right now, the chair you're sitting on, and the air you're breathing, all are results of a cosmic expansion that began approximately 13.8 billion years ago. The most robust data in modern cosmology shows that this is the age of the universe. However, when we point our telescopes to the most distant regions of the sky, we encounter a picture that seems to contradict the laws of physics. We find ourselves at the center of a vast sphere with a diameter of 93 billion light years. So if the ultimate speed limit in the universe is the speed of light, and our cosmic clock shows only 13.8 billion years, how is it possible that we can observe regions 93 billion light years across today? Today we will explore the journey of light through an expanding universe and understand why the universe appears observationally larger than its age. We say that the universe is approximately 13.8 billion years old. At this point, however, a direct and inevitable question arises. How do we actually arrive at this number? The reason is that we do not have a clock that was started at the beginning of the universe. Therefore, we do not measure the universe's age directly. We calculate it. Moreover, this calculation does not rely on a single method, but is confirmed by the fact that many independent physical processes converge on the same result. At the core of this process lies light. When we observe the universe, we are not directly observing space itself, but rather the light coming from it. However, this light does not reach us in the same state in which it left its source. Along its journey, its wavelength stretches or elongates, shifting it toward the red end of the spectrum. This effect is called redshift, and it is one of the universe's most fundamental measurement tools. Observations clearly show that the farther a galaxy is, the more its light has been redshifted. This means that when we look far away, we are actually looking into the past. These observations reveal that the universe is not static, but expanding. The relationship between distance and recession velocity shows that the universe is growing at a specific rate. From this, we can infer that if the universe is expanding today, it must have been smaller in the past. Tracing time backward, we see that all distances shrink, ultimately reaching an extremely dense and hot initial state. The calculation of the universe's age is based on this reasoning. If we know the rate of expansion and the current state of the universe, we can estimate how long this process has been ongoing. A simple approach gives roughly 14 billion years, but the universe does not expand at a constant rate. In the beginning, there was a very rapid expansion, followed by a slowdown due to gravity, and in more recent times acceleration again due to dark energy. This change is calculated using cosmological models based on general relativity, and the result is approximately 13.8 billion years. However, the reliability of this result does not come solely from theoretical calculations. The same value can be confirmed by independent observations. For instance, when we measure the ages of the oldest stars in the universe, we find that they are roughly 12 to 13 billion years old. This indicates that no structure is older than the universe itself, which is consistent with these calculations. Additionally, we can obtain information about time from the decay rates of radioactive elements, but one of the strongest pieces of evidence comes from the cosmic microwave background radiation. This light is the oldest electromagnetic signal to have reached us from the early universe, and its properties have been measured with extremely high precision. These measurements reveal the universe's age, density, and expansion history with remarkable accuracy. All of these independent methods converge on the same conclusion. The universe is approximately 13.8 billion years old. Therefore, this number is not a mere estimate, but the combined result of different aspects of physical reality. Yet this is precisely where the main problem arises. If the universe is truly 13.8 billion years old, and we know that the speed of light is the universal limit, then the farthest distance we should be able to observe would be about 13.8 billion light years. Light from more distant regions would not have had enough time to reach us. However, observations show that this is not the case. The radius of the observable universe is roughly 3 times that. The age of the universe and the finite speed of light lead many to assume that the maximum observable distance is limited to 13.8 billion light years. However, the critical mistake lies in oversimplifying the concept of distance. It is incorrect to imagine the Big Bang as an explosion occurring in empty space. If it were, galaxies would be scattered within a fixed space, and we could indeed only observe regions up to 13.8 billion light years away. In reality, the universe is not a static environment, but a dynamic structure that is constantly expanding and evolving. Galaxies do not move apart through space. Rather, the space between them stretches, driving their separation. Therefore, the familiar notion of fixed distance does not apply on cosmic scales. Even though a photon may have traveled for 13.8 billion years, the point from which it was emitted has continuously moved away from us during that time, and its current position is much farther. Here, it is essential to distinguish between two concepts: the travel time of light and the current location of its source. This distinction explains the vast difference between 13.8 billion years and approximately 93 billion light years. When we combine these three fundamental facts, the age of the universe, the distance light travels during that time, and the continuous expansion of space during its journey, we can understand how the observable universe can span as much as 93 billion light years. The light from the most distant regions started its journey much closer to us because the universe was much smaller at that time. After the light was emitted, the universe continued to expand. Consequently, by the time the photon reached us, its source had been moving away continuously. Step by step, a photon begins its journey when the universe is still young, and the initial distance is relatively small. As the light approaches us, the space it travels through also expands, meaning the source moves away at the same time and the distance keeps growing. As a result, the light reaches us after traveling for roughly 13.8 billion years. Yet during this period, the universe has expanded so significantly that the point from which the photon was emitted is now about 46.5 billion light years away. This distance represents the radius of the observable universe, and when considered in both directions, the total size reaches approximately 93 billion light years. It is crucial to note that the 46.5 billion light years refers not to the path traveled by light, but to the present-day location of its source. In other words, it reflects today, not the past. In summary, the age of the universe tells us how long light has been traveling, while the size of the universe indicates how much space has changed during that time. Therefore, there is no contradiction between 13.8 billion years and 93 billion light years. Rather, one is the natural consequence of the other. Beyond this, the question of why the universe has expanded in this way and why some regions are moving away so rapidly that we will never be able to reach them remains a deeper topic that modern cosmology continues to explore. In this vast cosmic stage, we have explored the boundaries of light and time together. If this journey into the depths of the universe has opened new doors in your mind, you can help more people access this knowledge by liking this video. Don't forget to subscribe to the channel and turn on notifications to follow the mysteries of space-time and the untold stories of the universe. See you in the next video, somewhere in another corner of the cosmos.